All right, let's get going. So we missed a day on last Wednesday. Sorry about that. Hope you guys enjoyed making snowmen and all that kind of stuff. Luckily, we actually did not miss any labs. I was mistaken and thought that we missed a couple of lab periods, but we didn't actually miss any labs. So labs are just going to kind of continue this week. And we don't really need to do too much catch-up, although today is, because labs start today, we're going to talk about some stuff today that you will probably immediately go into in the lab today. So I'll mention a little bit about that, and we'll go from there. Here's what we're going to do today. Homework 1 is due tomorrow night. Homework 2. Thanks, Bruce. Homework 2 is due tomorrow evening at midnight, or 1 minute before, I guess, technically. If you're having trouble with that, we do have a bunch of office hours today and tomorrow, and you can come in to do that. What I would urge you not to do is, if you haven't even started it yet, I would urge you to start it probably leave class right now and just go start it. No, if you haven't started it yet, or if you're kind of still at the beginning stage, there's a fair amount to do for it. So keep that in mind. But anyway, we're here to help, and if you do have specific reasons why you're not going to be able to hand it in, let me know, and we'll talk. So we'll do that. We will talk a little bit more about recursion, which is also part of today's lab. And then we're going to do the Unix tip of the day in a little bit of different order. You'll see why in a little bit. And then we will finally today talk about stacks. I believe, and I'm hoping this is true, that you guys did not cover stacks in Comp 11. You did cover stacks? You did not. OK, I'm getting some not. So you did not cover stacks. OK, so a brand new data structure, which is fun. So those of you who have been kind of like chomping at the bit to get to new stuff, there will be new stuff today. OK, I promise you that. OK, any logistical questions before I get going on comments on the homework? OK. All right, so here's what I have to say about homework 1. Well, there have been a number of questions about, there was a line in the description of homework 1, the handout, that said, don't touch the .h files. I'm relaxing that to the point that if you want to have your classes have other methods that you design that are like helper functions or helper methods, that's OK. Make sure they go in the private section of the .h file of the class, and then make sure you don't overdo it. And what I mean is every little line doesn't need its own function. OK? Yes, we try to make short functions that do like 1 or 2 things, tops. But you can kind of overdo it for some of this stuff. If you want to have a helper function that actually goes and expands your dynamic array, that's fine. We've seen the examples of that before, and that's perfectly fine. You can do that. But don't change the interface. In other words, what the person using your class sees has got to be exactly what we've given you in terms of the public member functions, and there's really no public data in that sense. So keep that in mind. OK, so anyway, you do want to do this reality check. Look, your helper functions can help out, but they can also make things a little more confusing if there's too many of them and you've broken your program too much. Let's see. That was really all I had on homework 1. Question?
So the length of our functions doesn't matter?
Well, no. The length of your functions does matter. You want them to be relatively short. I mean, I think, what was the Comp 11? 30 lines? I mean, you should keep it below 30 lines because, if you're writing functions that are longer than that, you're probably doing something wrong to begin with. I mean, even without helper functions, they should be less than 30 lines. I don't plan on taking extra points off if they're like 31 lines, right? Bruce probably would disagree with me on that. But my point is, make them as long as they need to be. Don't extend them too long. OK? You should not need to write helper functions to keep your functions under 30 lines. OK. Other questions on that? OK. Things going all right on the homework so far? People are OK with it? All right. At the end of the week, I plan on having a little poll to kind of see how you guys think so far about the hardness of homework assignments and labs and so forth. So if you have feedback on that, you can get that at the end of the week. All right. If there's nothing else on homework 1, let's see. Lab 1. As I mentioned, lab 1 is going to talk. It's actually going to be about recursion and stacks today. It's kind of a fun assignment. It's about solving mazes, and you'll get involved with that. I sent an email to everybody. Hopefully you got it this morning. The lab assignment today, it's kind of a lot of reading. So if you get a chance to download the lab assignment before class, just read it over once to kind of get a feel for what's going on. That'll probably help out a little in terms of getting up to speed on the lab. All right. Anything else? OK. All right. So a couple more things on recursion. So the other day, I guess it was last Monday, I mentioned this Fibonacci function. OK? And you guys have mostly seen it before. Oh, purple chalk today. There's also blue. You've mostly seen it before, but this is what we had written down for our Fibonacci function, right? Or at least something similar to this anyway. We said that the Fibonacci function for some integer n, OK, could be defined, there we go again, could be defined as the following. If n equals 0, return 0. Okay. If n equals 1, return 1. Otherwise, we're going to return Fibonacci of n minus 1 plus Fibonacci of n minus 2. And that was our function. And if you remember, the problem with this function was that we have this exponential growth of calls to Fibonacci. Because you call it here, and then each time this gets called, it calls 2 more. And then this one calls 2, and this one calls 2, and each one of these calls 2. And it just expands. Not a very good way to do recursion. Yes, it's beautiful. The mathematicians in us all will say, oh, that's a very pretty function in that sense, right? But not necessarily the best way to do it. Let me show you a slightly better way to write the Fibonacci function. Okay, and remember, the Fibonacci function is just going to print out the Fibonacci number 0, 1, 1, 2, 3, 5, etc. Where this is Fibonacci 0, this is Fibonacci 1, 2, 3, 4, and 5. Okay? All right. So instead of doing it this way, let's do some of the work up front, and then let's pass that information along to the actual next recursion of the function. Okay, let me show you what I mean here. Okay, and I think I briefly wrote this down, but we didn't quite get to it. Let's create a function called fibhelper. Okay, it's going to look somewhat similar. Okay, and it's going to have also an integer that you're looking for the Fibonacci number of. Okay, and it's also going to have 2 other parameters. Whoops. We'll call it partial 0 and partial 1. And those are the 2 where we're going to calculate the Fibonacci number such that they end up in P0 and P1. And that's what we're going to pass along. So we only need to do one recursive call at a time. Okay? So here's what it looks like. Fibhelper is going to do this. If n equals 1, we're just going to return P1. Now, I didn't really explain what P1 and P0 are. These are the actual, they're going to be the Fibonacci numbers that we calculate. Okay? This is going to be the prior Fibonacci number. This is going to be the one we're currently on. Okay? Bear with me on this one. If n equals 1, return P1. Okay? Otherwise, we're just going to return fibhelper of n minus 1, P1, that's this one, and P0 plus P1. Okay? And that is now our function. Now let's see what this one's doing. First of all, it's just checking our base case. In recursion, we always have to have some base case. Then it's saying, OK, return fibhelper of the integer we passed in, minus 1. And then the first, like if we pass in 0 and 1, what it's going to pass along is it's going to pass along the second parameter, P1. And it's going to pass along P0 plus P1 like this. And notice it's walked its way along fibhelper, or the Fibonacci sequence. Okay? So this one, if we call this with, let's say 5, 0, and 1, watch what happens. Okay? Let me write that somewhere where it makes sense. Right over here. OK. Let's say, read that for now. we call this with fib helper 5, 0, and 1. Okay? Let's see what this calls. This one calls, returns fib helper, I'll abbreviate FH for fib helper of 4, and then this one plus this one, 1. Right? And then this function, when it goes through and it gets to its recursion, it returns fib helper of 3, and then this one plus this one, 2. So far, so good. This one returns 2, and then 2, and then 2 plus 1, which is 3. And then this one returns, let's see, 1, 3, and 5. And then this one, because n is 1, we get to our base case. And this one says, OK, I'm done. I'm just going to return P1 here. So this one returns 5. OK? And the 5 gets returned to this, which gets returned to this, which gets returned to this, which gets returned to this, and out the door back to the calling function. We've only needed to do one recursion per function called each time. You see what I mean? So it's fewer number of calls to actually fib helper. And we've just passed along the data as we go. Okay? See how that's a little better use of recursion in this case? I wouldn't necessarily have expected you to figure that part out, but like the actual algorithm. But you can see that we can sometimes rearrange these to do a little more work for us by passing more information along. Okay, that's the big thing. Now, some people have said, hey, is recursion in general the best way to solve Fibonacci? I don't know. Let's try it without doing recursion. The dirty little secret about recursion is that you don't always you might have to jump through some hoops, but you can always turn recursion into a non-recursive solution. Okay? And for the examples that we're using, it's almost always, well, for the kind of what we call toy examples, it's actually sometimes better to do it that way. Okay? So let's see if we do this. And by the way, you can, if you don't want to, this looks a little ugly in some sense. You've got to know that you call 0 and 1 when you start out. You can write another function that calls this function and just pass it this and know that first thing it gets is P0 or 0 and 1. So you can do it that way. Let's write a Fibonacci function that's not recursive. Okay? And just see what that might look like. Int n. OK, well, let's see. We need a couple temporary variables ourselves, like P0, which will make equal to 0. It's going to look very similar in some sense. P1 equals 1. And then we'll also need some temporary variable as well. You'll see why in a second. This is how we set it up. And then it's just a loop, right? If we're going through this thing, it's a simple loop, right? I'll do it up here. OK, we're going to say for int I equals 0, I is less than n, and I plus plus, we're just going to walk through up to our number that we passed in, right, from 0 up to that number, well, 1 less than that number. Okay, and then we're just going to swap, we're going to do the actual algorithm, right? Temp equals P1. I need to store that because we're going to use it in a second. You can do this in some other order if you want. P1 equals P0 plus P1. And then P0 equals temp. Right? When we get done with that for loop, we're going to be at the Fibonacci number that we want. So we return P1. Okay? This is a simple loop version of the recursive algorithm, the algorithm that we had before. Right? It's actually fairly simple. Okay? I think I did forget one thing. Did forget our base case, right? So if n equals 0, return 0. And then that's it. And you can do it this way. So why did I show you that? The reason I showed you that was to say, look, we'll talk about recursion a fair amount of times. Recursion is not always the best solution. In fact, this would probably be a little bit faster than the recursive solution because you're not doing all these function calls, which is going to take up space, or it's going to take time to do the function calls, and you've got to save a lot of the current state when you're doing that function call. Okay, so that's how we would do it recursively, and like I said, it's not really any better to do it recursively. Okay, questions on that? No? Okay. I keep forgetting how quiet you guys are. The afternoon class is a little less quiet. Probably because it's still early. All right. So another use of recursion, I'm not actually going to write a bunch of code on the board here, and I forget if I mentioned it the other day. I don't think I did. There's a fun use of recursion to figure out if phrases are palindromes. Did I mention that the other day? I don't think I did. R-A-C-E-C-A-R, race car, right? That happens to be a palindrome, meaning if you read it backwards, it also spells race car, right? People have written like books that are palindromes. I mean, it's crazy how they've done it, but people have written like immense works that are actually whole palindromes. But you've got you can look at just simple words like this and see if they're palindromes either. Let's think about how we might do a recursive solution to figure out if that's a palindrome. Any ideas? Recursive solution? Or just a solution in general? Forget about the fact that I don't want to throw that recursion in there if you want to just describe how would we figure out if that's a palindrome or not? Yes? Yeah, check if the first letter and check if the last letter are the same. Okay, I mean, it's exactly the way you would do it in real life, right? Right, checking the first and the last. Okay. Can we break this into a problem that we can think of recursively? So you're going to do that. Then you're going to check maybe these two. And then you're going to check these two. And then the middle one, it doesn't matter. If it's an odd number, it's still a palindrome, right? So you're going to do that. Can we break this into a problem that's actually recursive? What might we do? Ideas? Yeah?
Can you pass in a smaller word without those outside letters?
Yeah. So race car is a palindrome, right? Because we checked the last letters. What if we lopped off the R's here and we just passed in A, C, E, C, A? Isn't that now a smaller version of the problem, right? But exactly the same idea. Now it's the same exact thing. And then this one would pass to the same function, our is palindrome function or something like that, C, E, C, and then that one would pass in E like that. That's how we would break this apart. Okay, so there's a number of little steps you have to do. You have to use your string functions to actually check and see if the first and last character of this string are the same. Then you need to break it into a slightly smaller string by lopping off the ends. And then you have to check the same thing. And when you get down to if the size is either 0 or 1, you're done. And you return true. At each one of these stages, if this had been like race cam, right, or something like that, right, the first time we would check this, and it would not be, we would not go and do the recursion. We would return false. Okay, so see how that works? That's a recursive solution to these things. Okay, all right, so again, bottom line, recursion is not magic. It's just another way of thinking about things. It's letting the compiler do some of the work for you, and sometimes it makes your functions easier to understand. Okay? And in fact, there are some ways of traversing various data structures that actually are easier not only to understand, but kind of in general using recursion, which we'll find out later in the year. Questions on recursion before we go on? The maze algorithm to solve the maze today that you'll see is kind of cool. I don't want to steal any thunder from the lab, but if you've got some maze where you're trying to find going through a maze, at each position, right, you can go one of how many directions? Normal mazes. You can go 4 directions, right? If you're here in the maze, you can go either north, south, east, or west, right? Well, if you do that, you can come up with a recursive solution that's actually very cool that says, OK, let's go north. And then that function goes north. And if it hits a wall or if it hits a I guess the end of the maze, it will actually go and then say, OK, well, now we're not going to go north anymore. We're going to go east, and tries that. And it's a very cool algorithm called a depth-first search, as it turns out. And it's kind of cool. But you can see a recursive solution to that. You'll see that on the lab today and tomorrow. Questions on that? No. All right. All right, let's transition into something a little different. I want to do the Unix tip of the day. Okay, the Unix tip of the day. There are two programs which actually come with Unix or Linux. Okay, and although I guess sometimes they don't anymore, but on your Mac, or if you have a regular Linux distribution, there are two programs. One's called DC, and the other is called BC. Okay, and let me just show you. I'm just going to start typing some things in DC, and I want you to see if you can figure out what's going on. Okay, DC. So I've just fired it up. Doesn't look like it's doing anything, but it is running. Okay, I'm going to type 4, and then a space, and then 5. And then I'm going to type the times key. And it turns out in this program, if you want it to actually give you like a result, you have to type P. Okay? And look what came out. 4, 5, star gives you 20. So far, so good? Let's look at another example. Let's say 2, 7 plus. I'm guessing you guys might figure out what that's going to return. Right? Yeah, I heard it, 9. OK. How about this? 4, 5 times, let's say, 3 plus. What do you think this is going to actually return? Any ideas? Sylvie? 23, right? It's going to do 4, 5, and then times that. And then it's going to do 3, and then plus. And it's going to return, oops, I forgot to do the P. It's going to return 23. Whoa. You can actually string these along, OK, and do lots of them. Let's do 3, 4, plus, 5, times, 2, 6, plus, times. I had that written down. I didn't just come up with that. All right? Don't try to figure out what this does. We will figure out what this does. But this is actually the same sort of calculation that we're doing before, right? And it happens to come up with 280. Now let's see what's going on here. OK, let me write this same one down, and we'll do it. OK, so we have 3, 4, plus 5 times 2, 6, oops, plus times. Plus times. OK. Here's what's going on. Okay? Now, by the way, while I'm thinking about it, this is what's called postfix notation. Okay? It's also called reverse Polish notation, RPN. Okay? And the reason it was originally called Polish notation is the guy who came up with the opposite of this, called infix, will happen to be Polish, right? They call this reverse Polish notation because that guy's idea reversed is Polish. And a lot of times you could buy calculators like this. The first like desktop calculators, maybe not the first, but some of the original desktop calculators that you could buy used this type of mathematics to actually do the calculation. So you had to know this format. Okay, it's called RPN or postfix notation. Has anybody ever heard of an RPN calculator? A couple people ever used one? No, yeah. You can use DC if you'd like and try it out, or you can just get I actually have I don't know if it's going to come up here. I have one up here that's on my computer that I use sometimes because sometimes it's actually easier, and we'll see why. By the way, two things about this. When we're doing this, we don't need parentheses, which is very nice. We also don't need to know orders of operations, right? Whatever order you do that in, you already know the order of operations you want, and it's going to figure it out. So this is actually a kind of a clever way of doing some of this thing. But let's see what happens here when we do this. Okay? All we're saying is 3 and 4. We get two numbers in, and then we apply some operator to it, right? So we do input the 3, input the 4. We get to this plus, and it says, all right, take these two and add them together, like that. Okay? Please correct me if my math is wrong on this. Okay? All right. Then it gets, and we've already used these 3. Then it gets to the 5, Okay? And then it gets the times, and the time says, OK, apply the times to these two, 35. Right? Then it says, OK, we've got a 2 and a 6. And we haven't done anything yet. So we actually are going to leave these guys where they are, 2 and the 6. Then we hit the plus. The plus says, oh, all right, do the operation on the previous 2. Like that, right? It's going to be 8. And now what we're left with is 35 and 8. And we've done the plus, and now we're going to get to the times. And we have a times in here. And then we do 35 times 8, which hopefully is 280. Is that 280? Hope it is. All right. You see how that actually works? You can string these out forever. Okay? And somebody came up with this calculator. This, Bruce, do you remember what DC actually stands for? Desk calculator. There you go. And you can do these functions like this. Okay? There is another version of the calculator. Okay? And let's see. Another version of the calculator called BC, which probably stands for basic calculator or something like that, maybe. I don't know. All right. BC is a little different. It actually allows you to do something like 4 times 5 plus 3 minus 6, which is, well, the way you'd normally do, like the way we would normally think of in what we call infix notation. I think I mentioned before that the Polish guy, I forget his name, did prefix notation, not postfix notation. And there's another one called infix, which is the ones we know. Infix suffers from the problem that you have to know what to do first, whether you do the times or the plus or whatever, and then you have to have these parentheses. Not quite as fun. The nice thing about BC, though, is it will handle numbers as big as you want, which means it's got arbitrary precision, it's called, right? So if we do like a huge number, like 1, 2, 3, Bruce gave me this example, raised to the 4, 5, 6, that's a pretty big number, right? Boom, right? It's a pretty big number, right? That number, it just keeps on going and going and going, right? And it just knocks it out, right, like that, because it's got the right code in there to actually use as much precision as you want. You do have to be a little careful on this. If you don't have the right flags when you do it, if you do 2 divided by 3, you end up with things like 0. Or let's say 10 divided by 2. Whoops, sorry, so that's not a good example. 10 divided by 3 gives you 3, right? So it actually truncates it. It doesn't have the precision. It doesn't have an automatic decimal precision. You have to actually type that in. But anyway, if you want to do large numbers with this calculator, you can do so. Okay? So that's BC, DC, and BC. Why did I show you that? Okay, why did I bother showing you that silly way of doing arithmetic, right? Well, turns out we're going to be using this idea of a stack to actually do some of those calculations. Okay? All right, finally we're on to a new data structure that is something you didn't see too many hands up when you said you hadn't covered or you'd seen it before. Okay? We're going to talk about these things that are called stacks. And you've all heard of like a stack of pancakes or a stack of paper or something like that, right? Stacks are named very well in some sense, right? If you have a, actually I'll make it a little plate, right? If you have a plate, like you're going to have pancakes on there, right? Okay? You're going to put pancakes on there. How do you put them on there? Right? You put a pancake on here, and you say, this is the plate, right? You're going to put a pancake on there, and now you've got a stack of 1. Then you put another pancake on there, and you've got a stack of 2, and et cetera, et cetera, et cetera. And let's say you're really hungry, and you end up with a stack of 4 pancakes like that. Remember, this is the plate. The first one looked like a pancake. Don't eat the plate. All right. So you've got this stack of 4 pancakes, right? What order do you actually have to eat them in? Well, most of you would like cut all the way through and then take a chunk like this, right? No, pretend you can only eat 1 pancake at a time. Which one are you going to eat first, right? You're going to eat the top one, okay? And then once you're finished with the top one, right, you're going to go and eat the next one down. And you're going to go and eat the next one down, et cetera, et cetera. This idea is called first in, or I should say, I'll do it the other way around. We'll call it last in, first out. Okay? In other words, with the pancakes, what's happened is the last pancake that you put on the stack becomes the first one that you take off the stack. Okay? That's my analogy for this with pancakes, right? Okay, the last one that you put on gets to be the first one that you pull off. Last in, first out, as it goes. Okay, and it's actually a really easy data structure. When we're going back to computers for a minute, because all you need to do, if you have a list, let's say, of numbers, something like that, right? Let's say you have a list of numbers, and our stack is going that way, right? You put a number in at the beginning, then you put a number here, then you put a number here, then you put a number here, right? We're always putting a number at the end of the stack. And when we take a number off, we're always going to grab from the last one. Okay, if we took that one off and then take that one off and then take that one off, we're going to grab from the last one. So it's actually very easy to build this data structure. In fact, all the lists we have already built, remember sometimes we have an insert at end function. Okay? That's or remove from end. I don't know if we actually did a remove from end. But if you did, that's basically a stack. Now, turns out that we call these special functions, right? If we're going to put a number onto the stack, we say that we push the number. Okay? Let's say some number like this. Okay? We say we push the number onto the stack. Where does it go? This was 1, 3, and that was it on our stack right now. We could then push the number on there, and it would be, let's say, 4. We're going to push it right on there. Okay? If we want to take it off the stack, okay, we actually say that we pop the number. And we don't actually know what number it's going to be. We're going to get a number. We're going to say get an integer that gets returned. We're going to pop it off what we call the top of the stack. Okay? There is one more function which is sometimes defined in some languages or some implementations. Other times it's not. If you just kind of want to peek at what's the last number on the stack or the top of the stack, there's a little function called top, which just says peek at it, but don't take it off. Okay? And I drew it sideways. A lot of times we will draw them up and down because it actually makes more sense. Okay? The thing about stacks is that they're such a simple construct, and they are so powerful for some of the things that we do in computing that they are implemented at like the very lowest level of the operating system, right? Or the computer architecture, actually. Okay, there's almost always a push and pop functions that are like kind of built into the low-level computer architecture on almost all architectures these days. And it's because it enables you to just store information that you're going to use again very quickly. Or you're going to use in kind of the reverse order. Have we seen any examples of stack-based behavior yet in class? Maybe 10 minutes ago. Yeah. Recursion, right? When you do recursion, all right, and remember my stupid example of recursion where it was like this, and then that called this, and you'd never ever want to do this because your program will segfault, right? Right? What happens is every time you get to this main function, there's a stack that saves all the data. Let's say we had a bunch of variables here, int a equals 2, et cetera, et cetera. All those variables get stored on the stack. Now, it's a little more subtle than that. You don't need to go and your compiler doesn't need to go, OK, where's all my variables? Push, 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 push. I mean, it's a little more subtle than that. But in essence, that's really what's going on. There's a set of data, or there's a part of data in your computer that's set aside called the stack. Okay? And it actually generally goes down in memory, but it doesn't really matter to that. But what it does is it enables you to keep that information. And remember, every time we return from some recursive call, right? When we return from a call, we have to restore all that state. And the nice thing is, if you push, 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 the way you get the stuff back is in the reverse order of all the stuff you pushed, which is exactly what we're doing with a stack. This first in, last out. That should say first in, last out model. I'm actually going to change it right now. I always get these mixed up. There's a couple of, there we go, first in, How about, yeah, first in, last out. Right. Or what did we say it was going to be, last in, first out? Well, doesn't really matter. Whoops. I'm going to say that. OK. Last in, first out, first in, last out. It means the same thing. It's just reversed. OK. So anyway, so that's how we're going to, that's why stacks are important, because they're used in so many different types of, computing practices, like when you're doing recursion, or when you're doing any kind of function calling. The stuff that the function that you're calling from gets all its stuff pushed onto the stack, and then when the function it calls returns, you get all that stuff back, and you just pop it off the stack. So it's actually pretty nice in that sense. Okay? All right. What are some of the uses that we can do that we will talk about for stacks? All right. Well, let's see. I don't want to throw a bunch of code at you today. In fact, if you go into the lab, when you go into the lab today, you'll see that there's a stack class that's actually built for you, but it's exactly like our dynamic array class, except that you can only push and pop from the end of the array. Right? I'm not going to worry about implementing those details, although you should probably just take a look at it. Okay, but what I want to do is I want to just go through a couple of stack-based operations that enable us to do cool stuff in such an easy way. Okay? The first one that I want to talk about is this idea of balancing like curly braces and symbols in, let's say, your program text. Okay? So let's take an example. Let me show you here. This is the one piece of code that I'll actually write here, right? Let's say we have an example that says if, and this is nothing particular, I just made it up out of nowhere, right? A pointer, some member x equals 2, right? Curly brace, C out, it's 2. Right? And then semicolon and curly brace. OK. Some of you guys use, I think you use Emacs or you use VI or whatever. You can type a little command that actually sees where your blocks begin and end, like your parenthesis blocks. Right? And so it's pretty easy to line things up. And especially when you have curly braces, there's like so many curly braces, you never know where you are necessarily, which one lines up where. Stacks are actually stacks are a very easy way to figure out if you've got balanced symbols. Okay? Here's the algorithm that we're going to use. Okay? Make an empty stack. So far, so good. We can do that. Right? Make an empty stack. Read the characters from whatever you're talking about, whether it's a file or on the screen or whatever. Read the characters in. Okay? If the character is an opening symbol, like an opening parenthesis or an opening brace or an opening curly brace, push it onto the stack. Okay? If it's a closing symbol, pop the stack. And if the stack happens to be empty, well, what does that mean? It means that, let's say we forgot this parenthesis. When we get to this parenthesis over here, when we pop the stack, there's nothing on there, so we've got to have an error. Right? Okay, so if the stack is empty, we've got an error. Otherwise, okay, if the symbol is not corresponding to the one you pushed on there, in other words, let's say we pushed a opening parenthesis, and then later on we got to a closed bracket. Well, what would that mean? It would mean we still didn't have things lined up. Okay, all right, and you go through the whole thing, and then at the end, you check your stack again, and it better be empty. Otherwise, we've left a symbol on there. Okay? All right. So let's actually go through this and do that. Okay? So we're going to start reading the characters. We're going to ignore anything that's not a brace or a bracket or a parenthesis, right? OK, so we're going to go along. We're going to ignore. We're going to get to this. We're going to get to this opening parenthesis. And we're going to push it onto the stack. So this is what our stack now looks like. Okay? I'm going up instead of sideways. Okay? Our stack is now going to look like this. It's got a left parenthesis on there. Okay? We're going to go through, ignore. We get to a left bracket, right? And we're going to push that on the stack, because anything that's a left, we push on the stack. Now that's on the stack. Okay? And then we go along and we ignore x, and we get to a right bracket. If it's a right bracket, we pop off the stack. Well, first we check and see. The stack is not empty. Okay? So then we pop the stack, and we compare, and we say, do the brackets match up? They do. So now that's gone. Okay, and we're good to go. We get over here, we get to a left parenthesis, same thing. We check, stack is not empty. We pop it off, we check and see if they're both parentheses. They are. Okay, we're good to go. Then we get to a curly brace, a left curly brace. We push that on the stack. Ignore, 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 until we get to the end curly brace. Pop or check and see if the stack is empty. It's not. We pop the stack, and we check, and we say our curly brace is the same. Well, only because I can't draw them. They're not. But they match up, right? Our stack is now empty. We get to the end of our file. We say, is the stack empty? The stack is empty. Congratulations. We have confirmed that our parentheses and our brackets match up. We've got them in the right order, and they've matched up. Okay? So in there's a possibility that Emacs or whatever uses a stack-based function to do that when it's calculating when it's figuring out where your braces are. Okay? Questions on that use of a stack? No? Okay. All right. So that was a pretty basic one, right? That was a pretty basic one. Well, let's go into talking about that postfix notation I talked about. Okay? It turns out that we also can use stacks to calculate postfix calculations. Okay? Here's the algorithm. Okay? All right, let me write this one down. This is the algorithm we're going to use for that postfix notation. Okay? All right. Read the number and read the input and push numbers onto the stack. Okay. Read input, push numbers. Okay? Until you get to a symbol or an operator. Okay? An operator is going to be like plus or times or divided by or minus or whatever. Okay? Push numbers, read the input, push the numbers until operator. Okay? When you see an operator, okay? Remember what we did, remember what the calculator was doing. It looked at the last two and said, oh, I better apply that operator to those two numbers, okay? Apply the operator. Apply the operator to the top two members of the stack. Okay? Apply the operator to the top two members of the stack. And then finally, push the result back onto the stack. Okay? When you're done with all this, what's left on the stack is your result. Okay? And that's all there is to it. Okay? Let's look at an example. Okay? Let's look at an example of doing this calculation. Okay? 6, 5, 2, 3 plus 8 times plus 8 times plus 3 plus times. Okay. I would not expect you to necessarily do that in your head. Right? Let's use a stack to do it. Okay? Here's how we're going to do this. All right. Read the inputs, push numbers until we get an operator. Okay, we can do that. Stack's going to be a little bit bigger right now. We're going to push these 4 numbers on there. 6, 5, 2, 3. All right, and I'll cross them out as we get to them. 6, 5, 2, 3. We've already looked at those. Push all those numbers onto the stack. Okay, we get to an operator. Pop the top 2 values, 3 and 2, and then add them. Okay, so we're doing the add. We're going to pop the 2 values, and we're going to add them. Okay, and then push the result back on the stack. Okay? So now our stack looks like that, 6, 5, and 5. And remember, we can only access this one. Okay? Unless you're doing something not stack related, you can only access this one. Okay? All right. So then we get to an 8. Well, what do? It's a number, so we push the 8 on there. Okay? And then we get to a times. And the times says pop these two and multiply them. Okay, we pop the 8 and pop the 5. We multiply them. We get 40. Push the result. Right? Okay, push the result. Then we hit a plus. Well, we get the plus. So it says pop the two values, 40 and 5, and add them. 40 and 5. And we add them, and we get 45. All right, and then let's see. We've got a 3. Push the 3. And then we have a plus. So we got to the 3, and a plus, and we're going to take the plus. We're going to apply the plus to the previous 2, 45 and 6, and add them together, and we end up with 48. Okay, and then finally we get to the times down there, and it says, well, there's 2 left. 48 times 6 happens to be, what, 288. So we pop off these two, multiply them together, push back the result, and we're done. So we've done the times, and we're done. And look what's left over, 288. Okay? That's a pretty simple way to do a long list of well, it's not really a long list, but a list of calculations. We didn't need to use parentheses. We didn't need to know any orders of operations. Okay? You just do them as you go along. Question, Rose?
What if that last multiplication sign hadn't been there? Do you just get left with the 2?
Yeah, we had a 48 and a 6. If the last multiplication wasn't there, you'd be left with 48 and 6 on the stack. And in fact, you can, if you printed a result, normally like the DC program would print the previous one on there. It would leave this one on there, but it would print the previous one on there. That's what a lot of times it does. Yeah, good question. Yes?
At what point do you pop?
So in this case, let's see. When you see an operator, apply the operator to the 2 top members. That's when you're doing the popping. So you had a 48 and a 6, and we got to the multiplication. You do pop, pop. So if you were writing this in code, I promise you I wouldn't do any code, but if you're writing this in code, you might have like int operator 1 equals pop, right? And then, I'm sorry, it should be operand, but we'll call it, I don't know, we'll call it number 1. Number 1 equals pop, and then number 2 equals pop. And what happens is that pops the top 2 values off, and then you multiply those together. Okay? It's actually, it really is a very straightforward and kind of a cool looking program when you write it and you go, oh wow, this is really easy stuff when you think about how much is going on behind the covers. It's it's relatively easy to understand in that sense. Okay, and this is how powerful it can be. Yes.
Do we have to write these functions for each version of stack, or do we make a stack if it's there?
Do we have to write the functions for each member of stack? All you have to write in your stack class, all you need are 2, maybe 3 things. You need a pop, you need a push, and you need a top. And the top is not necessarily required. Those are the only things you need to do. You would need to write the code to do this, but what you're doing is you're using the stack data structure to do the work for you, to store the stuff on there. Okay? Any questions on that one? No? Good. All right. Let's look at another one. And this other one is kind of cool because it leads into this one. But we need to do this one first, and I'll show you why. Okay? Let me erase this. So you're telling me, so you say to me, hey, Chris, look, I don't write in reverse Polish notation or postfix notation. I want to write a program that actually takes my regular input in my what's called infix notation with parentheses and all that. And I want to write a calculator to do that. And my answer is, well, you've already done all the work to make the postfix calculator work. Why don't we just convert infix notation to postfix notation? Okay? And there's some rules to do that, but you also just need to use one stack. Okay? So let's look at the following example. Okay? let's convert the following. And I'm going to use letters instead of numbers in this case. A plus B times C plus D times E plus F, there's a lot of letters here, plus F times G. OK. If we want to convert this from in-fix notation with the parentheses and the order of precedence and all, okay, into postfix notation, there's actually some fairly simple rules. They're a little more advanced than the other rules. But here's what I'll do. I'll write this. I'll do them in a little bit of shorthand. I'll say them out, but I'll do them in shorthand. OK. So here's how you do it. OK. One, you start with a stack, empty stack. One, empty stack. Actually, before we do this, yeah, question.
How do you create a stack?
Good question. If you already have a class, like when you get to the lab today, check out how you create the stack. Actually, you'll have to do that. So it's a good question. We have a class that's called stack, and we've actually created a class that's called stack. All it is a list where you can add to the end or take off from the end. Those are the only two things you can do for it. But it doesn't matter. It could be a linked list. It could be a dynamic array. It doesn't matter. Either one. But all it needs to be able to do is before, remember with our linked lists and our dynamic arrays, we could insert here, or we could grab a number from here. In the stack implementation, we've got to limit it to one place at the end. OK, well, 2, 3, 4. We can only do operations here. That's what makes it the stack.
So a stack can be a dynamic array or a linked list?
Sure. A stack can be a dynamic array or a linked list.
First in, last out.
Yes, it's just got to follow that rule. That's the invariant that I've mentioned before. The invariant of a stack is you can only touch the top value in the stack. You can insert on the top, and you can pop from this top. Now, does it matter that you can only do those things? No, you can have a list that does the other things, but you only need those two. And when you're talking about a stack, those are the ones we're concerned about. Okay, just the top values. Okay, good question. Before I even go on, are there any other questions about like the logistics of the stack? And by the way, in the lab, you'll see to create a stack, you've got a stack class, right? And you could do it as easily as that, stack S, right? If you've got a stack class that has a constructor that calls the stack, and then to do operations on it, you would do s.push some value and s.pop some like that. Like val equals s.pop. That's how you use it. Okay? You'll get some practice on in the lab today, but that's a good question. I kind of glossed over a little bit of that. Push and pop, only two things you can do. They have to happen at the end. Yes?
Why is it val against s.pop?
Good question. Pop says what? What is pop doing? It takes top one off, and then what does it do with it? It gives it to the value. Yeah, good. Okay? And the push needs the value to actually know which one to stick on the top of the stack. Okay? All right. And again, you'll kind of have to get used to stacks looking either up and down, because the kind of way we think of a stack, or side to side. But it's always going to be the top is always going to be the last part of it in this case. Okay? In a linked list, actually in a linked list, we might do it exactly the opposite. A linked list would probably do this. Our linked list implementation might look like this. If we've got 6 and 2 and 4 in there, right? Where do you want to push to make it easy on yourself? By the way, we have a head pointer. Let's say that it's not a doubly linked list. You can do this with a singly linked list. Where would we want to push the next value? Yeah?
You want to push it in front of the head.
Yeah, you want to push it at the head because you already know where this is. Was that what you were going to say as well? Whoever had their hand up over here, yeah. Same thing. You want to push it at the head, right? Because you don't want to walk all the way through and then push it over here. And then next time you want to pop, walk all the way through and pop. It's easy because you've already got a head. You just, boom, right here. Insert the next value right here, like this. If I want to push 5, I would take a 5 like this, and I would push it on here so that the head now points to there, and the first value is there, and the second, and all these values get shifted down. That's how you'd want to do a stack implementation. Not at the end. You'd want to do it right at the beginning, because it's much more efficient that way. OK? All right. All right. let's go back to this example here, okay, where we're going to convert this infix notation to postfix notation. Okay? I'm going to run you through the algorithm. The idea is basically go along, values get kind of thrown out, like the values get written down. When you get to these operators, you have to make some decisions about whether or not you're going to pull more operators off the stack. It's kind of the exact opposite of what we did before. Before we were pushing the values on the stack. Now we're going to push operators on the stack. So you'll see. Okay? We'll use the same stack over here. OK, so we start with an empty stack. OK? All right, if we have a right parentheses, OK? So if we get a right parenthesis like that, OK? Pop everything off the stack and write the symbols. OK? Actually, I should say this before we even do this. I don't know why I didn't have this one written down. 2. OK, empty stack. Read the input. OK? Writing the symbols. And in this case, the symbols are the A's and B's and C's and D's and E's and F's and G's, not the actual operators or the parenthesis. Okay? So read it, we're going to write down. So what we're going to do is we're going to go along, we're going to say A, and we're going to write down A, and that's going to be the result. Okay? All right, so we're going to read the input, writing the symbols. OK. If we have a right parenthesis, like that, okay? If we have a right parenthesis, pop the stack and write down all the operators until we encounter the left parenthesis. OK. So what we're going to do is pop, right, and then until we get a left parenthesis. Okay? You'll see how this works in a minute. If you have questions on it, that's fine, but you'll see how this actually works in a minute. OK. If we see any other symbol, I should say operator, any other operator or parenthesis, left parenthesis, okay, here's what we're going to do. We are going to pop the stack until we find one that's a lower priority. Okay? Pop until lower priority. You'll see what I mean in a minute. Okay? Pop until we have a lower priority. The exception is you never pop a left parentheses. You'll see what I mean in a minute. Okay? All right. When we get done with the output, we just pop all the operators out and then write them down. At end, pop, and write. OK, let's see what this actually means. Okay? And basically what we're doing is, did I ever get to a push? Hang on. I missed a couple things here. Hold on. If we see any other symbol, pop in the stack until we find a lower priority. OK, and then push the new symbol. So that's the one thing I forgot to do. Pop until any other symbol, pop until we get to a lower priority, then push. Forgot about that. OK, you'll see what I mean. This, let me show you what this is supposed to, the result, and we'll go and we'll see if we can get there. OK? The result is going to be this. A, B, C times plus D, E times F plus G times plus. OK. We'll see how we get there. This is going to be turned into this. Okay? And we're just going to follow our little algorithm. And all we need is this stack to make it happen. Okay? Basically what we're doing is we're going to get to operators. We're going to push them onto the stack. And the stack represents those pending operators. Okay? The ones with high precedence, in other words, in this case, times is a higher precedence than plus, just like it is in regular old arithmetic. Okay? All right. All right, so let's look at, and the parentheses are kind of the special case. Okay? It's basically like the left parentheses is high precedence when it goes on and low precedence when it comes off. Okay? You'll see. All right, so let's look at this and see what we do. All right. We first start out with A. Okay, and what I'm going to do is I'm going to cross out here and then write the answer down here. Okay, we start with an A. A is just a symbol. We're going to write it down. So we get to A, we write down A. Okay? Then we get to the plus. And we do the plus. Nothing's on the stack, so we don't have to worry about what's there. We're going to push that plus onto the stack. Okay? All right. Then we read the B and this. So we've got this one now. Then we read the B. Did I make this? Hang on. I want to make sure I did this in the right order. Then we read the B. Oh, and output it. Yep. Read the B and output it like that. Okay. All right. Now we read the star up there. Okay. When we read the star, let's look at what we said. It says read until any other operator or left parenthesis. Pop until we get to a lower priority, then push. The plus is a lower priority than the star, right? Than the multiplication. So when we get to the star here, we look and we say, what's at the top of the stack? It's a lower priority. Leave it there and push the star on. Okay, leave it there and push the star on. Okay. All right. Then we get to the C, and we read the C, and we say we push it down. All right. Then we get to the question.
I don't understand where, like in the program,
Yeah.
those output bits are, the A, B, and C, and where
Good point.
program those operators
Okay.
are.
Good point. And again, I'm not writing down the program because it's I'd rather just go through it. But this is an input string, so it's a string of letters and numbers that's just that you're doing the calculation on. So that's going to be input. You're going to be able to read that using a loop, one at a time. You read that, then you read that, then you read that, then you read that. So far, so good?
Yes.
Okay. So we're just going to read those. What we're doing is we're converting that into this. This is what we want to convert it into. We don't know this yet, but I'm just showing you. And what we're saying is when we get to letters, we're going to print them out. Or in other words, put them as the first thing. So we're just going to print them out in this case. Good question. Okay, so again, we read the A, we print out the A. Read the plus, push the plus on here. Read the B, print out the B. Read the star, push the star. Read the C, print out the star. Okay. Sorry if I was confusing everybody with that. Okay, we get that though? All right, good. Let's see. We left off at the plus. So now we've read all these through. We get to this plus. And we say, all right, that said, the thing says any other operator, pop until we get a lower priority, and we're going to print those out. Star is a higher priority than plus, so we need to pop it off. So we pop off the star, and we print it out. And then we say this plus is not a lower priority than plus. It's the same priority, so we leave that one on there. And then we push the one we just read in, like that. So we just read that one, and then we have pushed down there. So now this is what the stack looks like at this point. Okay? All right. Then we go and we read that left parenthesis. Now this is kind of that special case, right? In this case, when we read a left parenthesis, okay, we need to pop everything beforehand and print it out. Okay? So in this case, we are going to, let's see, we're going to get to here, and we are going to say, sorry, yeah, we're going to, hang on, let me read this. We're going to, highest precedence, so it is, sorry, it is pushed. The left parenthesis is the highest precedence, so it gets pushed on. Because it's the highest precedence, everything else is the lower precedence, so we leave it on there. Okay? Like that. Okay? All right. So here's what we have output now. I mixed up on the plus. Hang on a sec. That's what I did. Sorry. This is what's confusing me. Okay. Whoops. we had, let me go back to where we were. We had this, sorry for the confusion. Before we even read in the plus, right? Before we got to a lower priority. So we read in the plus, anything that's lower priority, until we get to something lower priority, we pop all these guys off. That's what it is. So we get to the star, we get to the plus. We read in the plus, and we say star is a higher priority. It better be output like that. Plus is also a equal priority, so it's not lower, so it also has to get popped like this. That's where it is. OK, so now nothing is left on the stack. Then we read the parentheses, the left parentheses, and we push the left parentheses. OK. Yes? Oh, I do need to push the you're right, thank you. I need to push the other plus that I just read. Yeah, I should have done it. This is a different example. Thank you. Still need to push the plus. Then we get to the other parenthesis. Because it's kind of the highest priority when it goes into a stack, we leave it. We don't have to push anything, or we don't have to pop anything else off the stack because it's lower priority. That gets pushed on there. OK. We read the D. The D gets just output. Then we read the star. OK. Star goes on here. The star gets read. And we say that this is now the lowest priority. So we're going to leave this on here. And we're going to push the star on here. Push the star. OK. We get read the star. Now we read the E. OK. And then we get to a plus. The plus says, we look at the stack and we say, what's higher priority ones? The star is a higher priority. So we're going to pop the star. Whoops. And push it there. Or output it. OK? And then we're going to have to push the plus back on the stack like that. OK? And we just read the. All right. Now we read the F, and that gets pushed. That gets written out. OK? Then we get to this right parenthesis. OK? And the right parenthesis is that special case, and it says if we get a right parenthesis, pop until we get to a left parenthesis. So we pop out. Did I do this one? No, yeah. So we get to we've gotten the F. We're getting to the right parenthesis. We pop everything off until we get to a left parenthesis. Because we don't have any parentheses, we actually ignore this one. And we don't actually write anything out. Okay. Then we get to the star. The star is a higher precedence than the plus, so it gets pushed on there. Okay. Pushed on there. And then we get to the G. We output the G. Okay. And then we're done. And our last thing says at the end, pop everything off and write it down. We pop the star, pop the plus, and we write down star and plus. OK. Why did I go through that whole thing to show you that? Two reasons. Oh, questions. No. Other questions on this? Yes.
So the left parenthesis
Yes.
began as a high priority and then moved to a low priority once it got out of the stack.
Yeah, the left parenthesis, right, exactly. So that you don't pop stuff off when you get to that parenthesis. Because what's going to, remember what's happening in arithmetic here, right? Things inside parentheses need to happen as a unit before the stuff outside. So you don't want to actually do any of the previous things until you've taken care of the parentheses. So that's really what it is. Versus low and high priority. OK, again, why did I show you this? Two reasons. First of all, to show you that stack operations can be pretty powerful. We just need to deal with the top of the stack. OK? And the second one is now that we've turned our infix notation into a nice postfix notation, we've already got a calculator that we kind of built earlier that's really easy to use to go ahead and do that. Is there a better way to actually do this calculation in one pass? I'm not sure of one. Okay, you do have to go through this stuff twice in order to actually do all the calculations. But again, it's kind of nice that once you've got it in this form, you've got it such that you can simply go through it with a very simple calculator, and all the precedence rules are out the window. Okay? There's a couple other things that are tricky about this. If you had subtraction and division, right? This one just happened to have addition and multiplication. If you had subtraction and division, you can do the same thing. You just make the priorities for subtraction the same as the priority for addition, and the division the same priority for multiplication. It happens to work out right when everything gets printed out. The one problem is you can't do things like negative values quite as easily. Because negative, like if you have a like -4, right? Well, that one's a little weird. You'd have to somehow have a special symbol to say, oh, it's a not subtraction, it's the negation, or the to make the number negative. So it's a little bit trickier there. Other operations you can do, there's, if you want to do things like operations that have just one, like the absolute value or something like that, if you happen to have an operation like that, you can do it in this way. You just have to build more rules into your little conversion program there. Questions on that? All right, sorry for the mix-up in the middle there. I read my notes wrong. All right. Anything else on the lab, the homework, or this stuff? We're going to do more stack stuff later. Stacks actually leads into the next stuff, the next topic, which we're probably going to cover, called queues, which now you don't have stuff at the top, just at the top. You can also pull from the other end as well. So it's a little bit different, but we'll do that. I think that's about all I've got for today. If there's no other questions, see you Wednesday or in lab.